Well, this is the time to find out the Laplace transformation of this function t to the power n. It's an interesting function because it generalizes a lot of things for us. For example, if we have a Taylor series in terms of the power of t to the power n, also known as the power series expansion, then we can take the Laplace transformation of the original function, which would be equivalent to taking the Laplace transformation of all the terms in the expansion, provided that that expansion converges. So this is enormously helpful for us, and in order to find out the general result, we would like to discuss something which is called the gamma function. Okay, now sometimes it's also known as the factorial function. So gamma function, factorial function, it's known in multiple names. So what is this function? Well, there are several ways to define this function, and the most useful way is to say that gamma function can be defined in terms of an integral. So this is capital gamma, and instead of defining gamma of n, we define gamma of n plus 1. Gamma of n plus 1 is most generally defined as an integral. So take the integral from 0 to infinity and then du. But the integrand is an interesting case. It may look unusual at the beginning, but it is very ubiquitous in functional handling. So we have u to the power n and then e to the power negative u. That's what a gamma function is. So just as before, in order to evaluate this, we take the limit from 0 to p, and then we take the limit p tends to infinity, and then we have what we have evaluated within this limit, and then take the limit p to infinity just to be sure that nothing unusual happens. Of course, this can be evaluated easily as follows. This is simply u dv, right? So e to the power minus u du is dv, and e to the power n is u. So we have limit p tends to infinity, and then first we have uv, so that includes u to the power n times negative u to the power minus u, and then we evaluate it from 0 to p. In the next step, we have minus v du. So v is of course negative e to the power minus u, and du is n times u to the power n minus 1, and that is integrated within 0 to p. I can take this negative sign outside, so this becomes positive. Actually, let me do it in the next line. So the next line would include limit p tends to infinity, and then if we plug in 0, then we simply get 0 here. So we should have minus p to the power n times u to the power minus p plus n integrated from 0 to p e to the power minus u to the power n minus 1 du. Now if we take the limit, we see that as p tends to infinity, e to the power negative p suppresses p to the power n. Alright, so this term, the first term goes to 0, but with the second term we have n, and then 0 to infinity, e to the power negative u to the power n minus 1 du. But notice this integral here in the second term looks a lot like the integral we began with, except instead of n we have n minus 1. So this is basically n times gamma of n. So for a reference value, we need to find out gamma of 1, and then by using the result we have just arrived at, we can build on that result. So gamma of 1 by definition is going to be limit p tends to infinity, integration from 0 to p, and then we have u to the power 0, which is 1, so I don't have to write that, then e to the power negative u du. Well, this is an easy integral. What happens is limit p tends to infinity and then minus e to the power minus u evaluated from 0 to p. Once we do that, we find this is just simply limit p tends to infinity, and then we have minus e to the power minus p, and then plus e to the power 0, which is 1. As we take the limit p tends to infinity, then the first term here goes to 0, and then we are left with 1. So this is interesting. We have two interesting results. One is gamma of n plus 1 is equal to n times gamma of n, and then we have gamma of 1 equals 1. So let's build off of these two statements. For example, what is gamma of 2? Gamma of 2 is gamma of 1 plus 1, and that is going to give us 1 times gamma of 1, which is just simply 1. What about gamma of 3? That would be 2 times gamma of 2, which is just simply 2 times 1. We can write that as 2 factorial. What about gamma of 4? What about gamma of 4? 4 would be 3 plus 1. That means 3 times gamma of 3, which is 2 factorial. And so this is 3 factorial. So similarly, gamma of n would be simply n times gamma of n minus 1, and so on and so forth. Eventually, we will arrive at n minus 1 factorial. Alright, and so this is why the gamma function is also known as the factorial function, because if n is an integer, which it is, we have seen at the beginning, then, well, let's say positive integer, then the gamma function is in fact the factorial function, and that's why it's equivalent of calling them that, but more generally, gamma function should be called as gamma function. So now it's a good spot for us to find out the Laplace transformation of t to the power n, where n is a positive integer. So n is positive integer. And what we do is to substitute t to the power n directly into our definition. So it's 0 to infinity, e to the power minus st, and then t to the power n dt. Now, one thing we can notice easily that it resembles a lot like the definition of gamma function. So to put it into the form of gamma function, what we'll need to do is to write down st as another variable. So this is equal to u. So therefore, t is equal to u divided by s, and dt is equal to du divided by ds. If we substitute them into our equation, what do we find? We find 0 to infinity, and then e to the power negative u, and then u to the power n divided by s to the power n times du divided by s. So if we take the s outside, what do we find? We find 1 over s to the power n plus 1, and then inside we have 0 to infinity, e to the power negative u to the power n du, which is really the gamma function of n plus 1. So we find gamma of n plus 1 divided by s to the power n plus 1. And that is the Laplace transform of the function t to the n. Now, one thing I'd like you to notice in this calculation is that this result that we have derived here is quite general. So nowhere in here we have used the fact that n is integer, right? So I could have taken it to show you that n, if n is not an integer, this is still true. And one of the example, or one of the most important Laplace transformation we'll have to find is that if n is half integer, that means some integer times half. Or for example, it's equal to minus half. Then it's interesting to find out the Laplace transformation because it's not so straightforward. To be more specific, so that you understand what I'm referring to, let's say I want to find out the Laplace transformation of t to the power negative half. Well, what we do in this circumstance is to substitute n equal to half into the result we have just found, and it would still be valid. So for example, in our case, we would find that it is going to be gamma of half divided by square root of s. Now, something that I wouldn't prove in here is that gamma of half integers have very interesting values. So for example, gamma of half is square root of pi. Now you might be asking the question, how can we find pi or square root of pi out of a function whose result for integers are factorials? That doesn't make any sense, but it does. And in a separate video, I'll explain this by the form of Gaussian integral, but that is not relevant here because I'm not explicitly showing it to you, but I'm just giving you an information and the fact that it is still doable. And so therefore, if I want to write the result, it's simply pi over s square root. So that's an interesting case. This is also interesting for other reasons as well, because this particular function t to the power negative half doesn't also satisfy the condition for the existence of Laplace transform, but it's still doable. So it's one of those examples where the sufficiency of the conditions of Laplace transformation means that the transform exists, but if the transform exists, then the conditions are not necessarily satisfied. If you want to understand what I'm referring to, please go to the previous video where I've spoken about the conditions of the existence of Laplace transformation. So this is one of those cases where we find an exception. Apart from that, this is the correct result.